Okay, so this is gonna be one video, and this video I've been wanting to do for a while because this is, one of the subjects I love the most and I study the most. I've been passionate about this since I was a kid. So the video is this. Today I am gonna teach you, or not teach you, maybe talk about one of the many ways we've been improving internal combustion piston engines. You may think, we've been using piston engines since like forever, nothing has changed, it is still the same reciprocating engine that we used on the 1940s and stuff like that. But the thing is that engines today are more efficient, more reliable, and higher power for smaller engine and less fuel than they were 10 years ago, 20 years ago, 30 years ago, 40 years ago. Like if you look at a 20-year block in time, let's say from the 1940s to 1960s, 1960s to 80s, 80s to 2000, 2020, and 220 and beyond, you are gonna see that engines became way more efficient, less polluting, more reliable, smaller, and the benefits have been increasing over time steadily. And one of the reasons why I wanted to do this video and why I wanted to talk about one of the improvements that we've made recently and that we're gonna have more on the future of internal combustion engines today is because yes, electric cars are gonna take over. Yes, electric cars are way more efficient and way less polluting than internal combustion engines. But that doesn't mean that we should make today bad internal combustion and inefficient internal combustion engines. Internal combustion engines have its place on the world today. And today we can buy and make very efficient engines. And if you don't make as a company, and if you don't buy as a consumer a high mile per gallon car or engine, is not because you don't have the option. It's just because you don't like that particular car or that particular engine. Because, many companies have come up with many different ways of implementing this. Some are better than others. Some are more reliable than others. So let's get started. I don't know how am I gonna divide this. I am gonna divide it. So I am gonna do this. There's three parts of an engine. There's the intake and camshaft assembly. Then there's the block and the compression ratio and the stroke. And then I'm gonna talk about external compression, which is mainly gonna be turbocharging and types of fuel and how you can ignite the fuel and the chemistry about the fuel. So that's a good idea. The block, then the head, and then the externalities that you can have on your engine to improve the efficiency. So let's start with the block. Let's start with the block. So one of the ways that we've improved fuel efficiencies inside of the block of the engine, mainly it's two things. On the olden days, it was better manufacturing and better standards for pistons and piston shape and form. For example, pistons on the top can be flat, can be like bottom out, can have like a crown shape. All of this is mainly to change the compression of the engine. So So now, okay, so I'm gonna put it this way. When I talk about improving the efficiency, just on reference to the block, the two most important things that you can change on the block to improve efficiency is what is the compression ratio on the engine and what type of stroke and force you can get out of every cycle of the engine. So a higher stroke and a higher lever that the rod can have on the crankshaft, it's higher efficiency. The other thing is higher compression ratio. Now, on the past, we've improved engine efficiency on reference to the block, mainly by improving the compression ratio, because there are hard limits on what you can do to improve the lever act and the friction on the side of the pistons that you get from a longer stroke. Longer stroke really hasn't ever improved efficiency of one particular engine. It has made it that there are super efficient engines, big diesel engines, long stroke, and non-efficient but very compact and very cheap short stroke engines in comparison. So on the stroke side, we really haven't been able to improve efficiency given a same engine, but there have been different engines of different sizes that have taken advantage of a longer stroke for increased efficiency. The other one, the compression ratio. Now, why compression ratio improves efficiency? If you have a higher compression ratio, it means that when you're at the top of the piston, the ignition of the fuel and the air, it's gonna be at its peak force and peak pressure. And the higher and the smaller the space, the more power it is gonna exert and the longer it's gonna exert it on the piston as it goes down. So let me put it this way. If you have a cylinder volume like this, and you only compress it half, inject 1 drop of fuel and ignite it, it is gonna only utilize a certain the half of the space for that 1 drop of fuel to make power. Now, if you utilize the full cylinder, put the same drop of fuel, and then ignite it, you're gonna basically have double the travel on your engine. Now, again, there are hard limits on how much compression ratio you can have. The main reason is because of knock and heat management. So what is knock and what type of heat I'm talking about? Knock happens when via given mixture of fuel and air, you compress it so much that the pressure and the temperature become so high that it reaches ignition either temperature or ignition pressure. And if this happens before the piston gets to the top and starts going back, let's say this is the movement of the piston, right? Well, up and down. If your ignition of the fuel and air happens when you're going up like this, that is called knock. And knock is very bad for the engine. And knock happens because your compression ratio is too high. Usually you don't have to worry about that in an engine that you buy because it's been engineered in a way that doesn't have that, with some exceptions. But yeah, the higher the compression ratio, the more likely it becomes that the fuel is gonna ignite before you reach the top. Now, today and for the future, what are things that we are improving on the block of the engine? Well, the first one is size. Engines, not on cars, but industrial applications and ships and generators and stuff like that, they have been getting a lot bigger. And two things that come to my mind right now. Is one thing. One thing that I know that has been improving the efficiency of piston engines today is that on big marine diesel engines, the main rod of the piston is no longer connected directly into the crank. It's actually connected to a middle rod, and then that rod is connected to a crank or a crank shaft. Now, the advantage that this can have is that the crank shaft and the middle bit can have a very long levering act. Like it can be like gigantically big. You have no limit on how big it can be, because first, the cylinder wall, you're never gonna touch it since this thing moves parallel to the piston. And then this thing on the bottom is connected to the crank. And the piston is connected with a rod to the middle crown. I forgot what it's called. But put it simply, it's basically like a double piston setup, but one piston only has to deal with the actual ignition forces and pressures. The other one is really just like a guide. It just moves up and down with the piston, and it's directly connected to the crankshaft. That improves the efficiency by quite a bit. As again, because I said the size matters when we talk about stroke and levering at, and the other one in which way improves efficiency is that because this is a guide, friction losses with the sidewall of the piston become much less, since the crank is never pushing the piston to the sidewall, since it is not directly connected to the crankshaft. That's one. The second one, this is applicable to smaller engines, and it's being applied today and for the future. Because, so it's being implemented today in only some cars, and it's planned to be implemented on the future on more cars. And this one is offsetting. So this is the crankshaft. This is the piston line, the middle of the piston, right? Usually, the center of the crankshaft and the center of the piston perfectly line up. But on some modern engines, the crankshaft is offset to the side. Now, why would it be offset to the side? The piston moves exactly the same. The crankshaft rotates exactly the same. But if the crankshaft, the center of the crankshaft, it's offset to the engine, the rod, it's always gonna be at an angle, even at top dead center, and at some points it's gonna be more angle, and at some points it's gonna be less angle than if the crankshaft was exactly at the middle. Now, how does this help? If you change the timing so that the ignition and compression of the ignition of the engine happens when the rod, it's more kind of like, instead of the rod going completely sideways, since it's offset a little bit, it has like less of an angle, you get higher efficiency, because again, the engine, it's gonna push less the piston to the sidewall. And second, by being at an angle, the speed of the piston, it is gonna change at certain points compared to a completely centered crankshaft. And it benefits on the way that the piston moves more slowly at the top when the ignition happens, and moves faster at the bottom when nothing happens. And that improves efficiency because, again, everything happens when the piston is at the top. What happens at the bottom is completely almost irrelevant. You have to get most of your power and most of your fuel and ignition when the piston is at the top. And an offset crankshaft provides you less speed when the piston is at the top, which improves efficiency. The first one I talked about, big marine diesel engines, again, that's been implemented on marine diesel engines and big generators, industrial generators, that type of stuff. Offset crankshaft, it's been implemented today mainly on the Toyota hybrid drive. So any Toyota hybrid 4-cylinder that you buy today has an offset crankshaft. That's been one engine drivetrain that they made since 2017 that they've been implementing to like all of the cars that have it. Toyota used to have a 4-cylinder hybrid that they had on the Prius, but the newer Corollas, the Prius, the RAV4, the Sienna, all of those cars that come with a 4-cylinder hybrid have an offset crankshaft. And the third thing, I guess, that improves efficiency in relation to the crank stuff is something called an Atkinson cycle. Usually on an Otto cycle engine, which is pretty much almost every engine today, the piston draws on the intake stroke. It is gonna draw the full volume of air, and then it's gonna compress that full volume of air and ignite that volume of air, and then exhaust it, and then intake again the entire duration. Now, again, compression, the important thing here with Atkinson cycle is this. The compression is the limiting factor. We can compress the air and the fuel to a certain point. At one point, you cannot compress it anymore. But there's like a small cheat that you can do with a non-variable piston movement to increase the efficiency or increase the compression ratio of the engine. What you do is this. Instead of drawing air for the full duration of the intake stroke, you draw air from here to here, don't draw air, and then compress it back again. But when the ignition happens, again, you have the full travel. So you only intake a certain amount of air, compress it much more than you would have been able to compress if you had the entire intake full volume of air. And then when you expand it, since the piston moves the same amount, when you expand it, it's going to be more travel than the intake stroke. This is called Atkinson cycle. Atkinson cycle used to exist since it's an old idea, but it was never implemented properly on an engine because mostly from like the 1950s to the 70s and 80s, the important stuff was reliability. Reliability and power was the main important thing that we needed from engines. And really, Atkinson cycle, before today's implementation of implementing it just with the camshaft, they were used to be where the crank to move in an eccentric way to change the compression and the intake and compression ratio of the intake and exhaust expansion ratio of the engine. It used to, so put simply, it used to be done with the crankshaft. Toyota does it by changing the intake stroke. So in reality, it's a change of the heads, not the body per se. But Toyota implemented both the Atkinson cycle and the offset crankshaft, which both benefit a lot to improve efficiency. That's why, Toyota is very famous to making very efficient engines. And With both of these, there are disadvantages. I'm gonna just briefly go over them because I have to cover more stuff about improving engines for the future. Disadvantages with the Atkinson cycle. First of all, the way it's been implemented today on the standard Otto cycle engine is this. Your valve seats and springs and pressures and leaks are more profound because you're cheating basically. When the cylinder is pulling a vacuum and forcing air inside, you're closing the valve and saying no, stop here, but the piston is gonna still move. So you're affecting that the piston has a pulling force on it, and that affects the reliability and the balance on the crankshaft. And it also affects that you're actually pulling and putting a force on the valve seats and on the valves themselves that the springs have to overcome to actually close it properly. Now, Toyota has solved this problem by using hydraulic pressure valve springs, as far as I know. I think they use both. They use springs and they use hydraulic pressure to properly close the valves. The second one with the Atkinson cycle, with the offset crankshaft, is that again, the balance goes off the table because when there's a center line and everything is centered together, basically there's like a single rotation pressure, a single weight that you have to balance on the crankshaft. But when it is at an angle, that moving piston, it's unbalanceable just with crankshaft weights. So affecting the balance of an engine affects the reliability, which can be overcome by just spending money on better materials. But it's a balance. It does affect reliability, it does affect the performance of the engine, but Toyota has made it so that it's less relevant since basically the engine is no longer directly attached to the movement of the car since it's a hybrid, and that improves things quite a lot. So that covers the Atkinson cycle and the offset crankshaft. Now, let me talk about the camshaft. Now, what does the camshaft do? The camshaft basically puts air into the engine. With that, I think I'm gonna tie in direct injection of fuel, or fuel injection, let's call it that way, with the camshaft stuff. So, how from the past we improved efficiency for today when we talk about the camshaft and the fuel injection? First of all, we've improved the shape and the way air and fuel is directed into the engine. That if you have a better mixture of air and fuel, it is gonna burn much better and much cleaner, which is good. That has been implemented since the invention of fluid dynamics, pretty much, because before that, it was just whatever you can manufacture and cheaply was implemented to the engine. But since the invention and the study of fluid dynamics on computers and 3D modeling on computers, you were able to predict and improve the efficiencies of how to mix and put air into the cylinder stroke through the valves and through the intake manifold, basically. On the valve side, how you open the valve, for what time you open the valve, has always been very important for the efficiency of the engine, because the more air and fuel it allows to pass into the cylinder, basically the more of the cylinder you're using to actually do work. Because if the cylinder opens this much, but it has a negative pressure inside because your valve didn't open as much, or it doesn't open properly, or like the speed of the opening and the closing is too fast that really the pressure and the fluid movement is not enough, then there's no point of having a long stroke and a high compression ratio if really you're never going to be able to take advantage of it, because the way your valves open is never enough to allow proper intake of air and fuel. Now, on the past, there's been many ways that we've improved this. First of all, we passed from 2 valves on every cylinder to 4, because a smaller diameter circle can fill out a bigger diameter circle with more efficiency than a bigger diameter circle. So 4 valves allows more flow inside and outside than 2 valves. So we passed from 1 exhaust valve, 1 intake valve to 2 intake valves, 1 exhaust valve to 2 and 2 today, which is more efficient. Another thing that improves efficiency that is been changing over time is how much the valve opens and at what time it closes and at what speed it closes and opens. This has been changed with time, with better efficiency on like materials for the seals and the springs, and also with the invention of variable valve timing. So Honda, very famously for performance, has VTEC, which basically is just a system that opens the valve further down into the cylinder head to allow for more air and fuel to pass. This is not precisely to improve fuel efficiency, is to improve more power, because one of the limiting factors on a revving engine, especially when you reach very high revs, is that there really isn't just much time available for a negative pressure inside a cylinder to draw in air through the intake manifold. So being less restrictive on the valves becomes a very, very important factor. That's why most race engines have very, very aggressive valve lobes on the camshaft that are terrible for reliability of the springs and valve seats. That's why race engines and regular engines have very different timings and camshafts because of this reason. So variable valve timing, that's one way that we've improved the efficiency on past cars. Now, to this day, we still are improving the technology of variable valve timing. One of the examples is Ducati has stubbornly stuck around with no spring setup for the timing of the engine, which no spring means more efficiency, since the spring is connected to the camshaft is connected to the crankcase, and it's very simply put a parasitic loss to try out to the camshaft to compress a spring, pretty much. That is not exactly variable valve timing, but it is an efficiency, a technology gain per se, that Ducati has stuck around with. Honda, the VTEC technology, they've improved it with the years. Many other companies, for example, I said Toyota. Toyota implemented the timing and the variable valve timing and change it in a way to provide the closing of the valve while the cylinder is still intaking air to do the Atkinson cycle thing. So that's one way the timing of the valves has been changing. Before I talk about the future one, I'm gonna talk about the fuel injection. When you control the timing and the amount the valve opens and how much air it provides to the cylinder, it is very important that you manage the fuel properly, because if you know for a fact that you are putting more air into the engine, then to make more power, in theory, you can put more fuel. Or if because of emissions and blah, blah, blah. Well, okay, I'm not going to talk about that. I'm only going to talk about if you know for a fact that you are putting more or less air into the cylinder, you can also immediately change how much fuel you are putting in or you are not putting in. And the only way that changed and improved the efficiency on the past is because we passed from carburetors which are passive, non-modifiable, just have a vacuum inside a tube and the fuel flow is going to manage itself, to port injection and direct injection. Now, what changed with port injection at the beginning and then with direct injection afterwards? Fuel injection, it was computerized, and with computers you actually then change the timing and the duration of the fuel valve opening, and that let you change how much fuel you put it into the engine. So with the introduction of variable valve timing and variable air, let's put it that way, inside of the cylinder, it was very easy to manage fuel, to have fuel management, because we knew whether the engine had more or less air. And that was one of the ways we improved reliability and fuel efficiency of engines in the past. Now for the future, valves have been changing. So on the, not just valves, I'm gonna tie it up with fuel injection. We really were upon a golden age for head design and camshaft timing and electronically controlled fuel intake, fuel management, and fuel ignition. As I said, on the past, it was very passive. With carburetors, you didn't even change anything. It was just, as long as there's some vacuum on the intake, fuel automatically is gonna go in. You controlled nothing. You only controlled the butterfly opening for the limit of air. Now, then it changed so that we sort of controlled fuel, and then with the valve timing, we sort of control air. Air. But it was separately controlled by computers, but never properly implemented to maximize efficiency. It was kind of separate systems per se. It was never properly tied together in, especially when you take into account spark ignition. Those three were kind of always treated separately. We're never completely tied all of three of them together. But with computers becoming much, much better, more reliable, and cheaper, we really were on a precipice of engines becoming super electronically controlled to the point where you could do things that you weren't able to do before. And one of the examples that I'm going to give tying to the fuel injection is this one. The name that they put to it, it's hcci, which means homogeneous charge compression ignition. Now, anyone that knows anything about engines is gonna know that it's basically a diesel engine. Diesel engines have super high compression ratios, have a glow plug that basically you have a massive intake of air, as much as you want, or the engine is capable of doing. You compress it as much as you can, and then directly inject the fuel into the super hot spark, the glow plug, and into the cylinder head. and let the fuel burn, pretty much. Automatically, pretty much self-ignition. And hcci engines with gasoline were on the precipice of being manufactured by like every company. And the reason why they didn't exist before it's because with hcci you had to have perfect sensing and control of how much air was gonna go in, because it was gonna compress it to the point where if you had port injection of the fuel and mixed with air, it was gonna self-ignite. So on gasoline engines, they controlled the variable valve timing of the engine depending on the engine speed and throttle position. Also, they needed to control the exact point where it was gonna spark, because it did have a spark plug. Even though it was a homogeneously charged compression ignition engine, it was still gonna have a spark plug, because the idea was that just before the engine reached top dead center, where you knew it was gonna self-ignite, you ignited the spark plug, and at the same time you started spraying more fuel to make the mixture a little bit richer on the fuel. And then by the time everything ignited properly, or everything self-ignited, it was gonna have reached top dead center, and the piston was gonna start to go down. All of those things had to be perfectly controlled in order to have proper diesel functionality on a gasoline engine. And this was implemented on, again, one of Mazda's very unfortunate timing stuff, because Mazda implemented this. Probably they researched this by like the 90s and 2000s, and they had it working on an actual production car. I think it was something like 2000. They announced it on like 2012. They implemented it like 2015. They only sold it though on Europe, which is kind of funny. I don't know why. You can look for Mazda Skyactiv X, and it was this technology implemented into an engine. It was way more fuel efficient than just regular ignition engines. But, I've talked before about Mazda's bad timings with technologies, and this is like one of them. They made this technology just as electric stuff was coming around and it was becoming cheaper, so it was gonna be hard to sell to the masses, pretty much. So that's variable valve timing and the fuel injection. Let me see. Now there is another one. Depending on the speed the engine is going, and depending on the... So going back to the Atkinson cycle, where Toyota closes the intake valve before the piston reaches the bottom, or it keeps it open for longer during the compression stroke, so that you have a difference in the intake and the exhaust. You can accomplish that not by just changing the timing of the valves, but also the duration of the valve. And that provides for a more compact engine and for a... Everything is tied together, but basically it's this. Changing the duration of the valve is also important, because the valve being open by just like nothing, like a few micrometers, it's irrelevant. It's pretty much closed. It has no airflow on it. The valve is only truly open like for half of the duration of the lobe, pretty much. So having a change in the speed of the lobe so that it opens the valve for more time or less time was also very relevant for variable valve timing. Now, the problem why variable valve timing was so massively introduced and variable valve duration was not is because reliability. Again, the same idea with the crank shaft being offset from the center of the piston. It has a slight impact on reliability. How you make the lobe of the camshaft to change speeds when it is touching the valve, there's only two ways to do that. Now we're going to talk about the future. One is if you have a completely electronic or separate mechanical drive system to move the valve. So, for the future, Koenigsegg invented or created, whatever you want to call it, a fully electronic valve control system, which is very impressive on its own. But Koenigsegg has made some very ridiculous cars that only like 2 people can buy. So even though very cool, I don't think it's gonna ever be sold to the masses like you and me. But it is very cool, and it proves the point that if you have a disconnected from the crankshaft with chains and stuff, the valve, you can have way more power and way more efficiency. The other one, when you don't have an electronic or mechanically disconnected valve system from the piston turning, is if you have an eccentric turning camshaft. There's many ways to implement this. The most famous one today is Hyundai. Hyundai made a camshaft that they called CVVD, which is continuously variable valve duration. It is kind of a gimmick because this has been created before. It's just Hyundai has actually put it in a car that many people can buy. It's the 1.6 turbocharged engine that they used on the smaller cars. And the idea of how it works is this. Usually, this I have to draw. So, when you have a circle that's connected to a bigger circle, right? And this turns this way, the velocity of this circle, it's always going to be constant, no matter, oh yes, you can see, no matter at what position this is looking at, or at what point in the 360 degrees this is, the velocity at which this point is moving is always going to be the same because it's just connected directly to the circle. Now, how you make a circular turning thing have a variable speed on another object? Well, you slide a line through the circle. So let's have a circle with the pin, but instead of the pin, instead of we moving the pin, we attach a rod like this that's able to slide, right? It has a sliding space, and this rod continues, and at one point you connect it to a solid pin. So what is going to happen? As this circle turns, this is going to move like this, right? Now, the speed at which this moves up and down is never the same. So this is basically a variable speed mechanism connected to a stationary or a single speed moving object. Now, how you implement this on a camshaft, it's a little bit more complicated, but the principle is the same. You're gonna have a sliding pin, basically the lobe that presses onto the valves. So this is gonna be the valve, right? The lobe that is gonna press against this, it is gonna be disconnected from the actual turning of the camshaft, and it is gonna be on a mechanism of a sliding pin connected to a stationary rod. So all of this is implemented inside of like a camshaft mechanism, and that way you have a lobe that at a certain position, like here and here, it is gonna have a different speed than from here and here, with the idea of this having different speed at this point than at this point. Now, this is how Hyundai applied the continuously the CVVV on the new engines. This was created before on a production vehicle too by a British company called Rover, and this was on the 1990s. It was a different mechanism though. It was not exactly the same as Hyundai's, but this was used before. And well, I mean, we kind of know what happened to British cars. They sort of never caught on. But it was a technology that was used for the same displacement of the engine and basically to have the same engine, but just by changing the camshaft, have either more power or more fuel efficiency or more responsiveness. So this is one of the future technologies that was going to be implemented more, if not for the Tesla. What else? So that's Hyundai and Rover. I covered Koenigsegg, the offset crankshaft, Atkinson cycle I covered. Now, let's talk about finally the outside of the engine. Turbocharging cars, even though they were invented very long ago, and even though today people think of it mostly on the term of more power, in reality, turbocharging cars, it can tie together with more efficiency because it is a cheat that you can have to increase compression ratio. So if you have a particular engine, right, a particular size and displacement, and you don't have turbocharging or supercharging, basically this is the amount that you're gonna have, and you're gonna compress and you're gonna ignite. But if you have forced induction, if you have a constant higher pressure on the intake manifold and you open the cylinder, basically when you close it, you're gonna have a higher compression and higher pressure, even though the compression ratio is the same, because you started off with a higher pressure, not a vacuum. And forced induction is a way to cheat the limits of the compression ratio equation that an engine has. Turbocharging, it's a very good way to increase the pressures inside the engine. And even though at the beginning it was very famous for being unreliable, the reality is that turbocharging by itself doesn't change anything about the engine. It just makes the engine run a little bit hotter, which is a problem, yes. But if you properly manage fuel, if you properly manage heat, and you properly manage materials, really turbocharging never has to be a problem. And that's why cars today, many cars are turbocharged because it increases efficiency when properly tied with the engine management, and it comes at the price of maybe a little bit more expense since the engine has to be more engineered a little bit better. But turbocharging is very good when tied in with compression ratio, and also when tied in with self-ignition, which is on a diesel or in an hcci engine. And that is also something on the future was going to be changed way more since if electric cars had not come around. So yeah, that's it. Those are the subjects that I wanted to touch that internal combustion engines did change a lot during the years, and we were seeing changes today too, maybe not as fast as before or maybe not as dramatic as before, but they were changing. They were becoming more reliable, more efficient, better in general with new technologies. It's just the electric technology was just so much more cheaper and better if implemented properly, that we've reached a point where investment on internal combustion engines, especially on cars, is just not going to be, is never going to be implemented more. What we see today, it is probably going to be what we're going to see on 2030 and 2035. And after that, really, by my opinion, more than half the vehicles on Earth are going to be electric vehicles. So there really is no point for any company to invest in better internal combustion engines or more efficient internal combustion engines. One of the last ones that is kind of good is Toyota one. The one from Toyota is actually incredible, but it is half electric. So at what point you say that the improvement of the internal combustion engine is relevant there? I mean, I don't know. It's kind of like based on your opinion. Mazda wants to do a similar thing. Mazda has been on the news because they want to implement a new rotary engine, but as a generator for an electric drive. And again, Mazda with its stupid timing, because Toyota was there with the Prius on the 90s. So they're 20 years late, which is stupid as fuck. They haven't produced a single one of it. And then they want to produce this rotary hybrid drivetrain for the future when it's already been proved by Toyota, which beat them, that the future is not hybrid, it's fully electric. Toyota has basically admitted that electric is better. Hybrid doesn't work. It's just worse than fully electric. So Toyota has announced that they want to make fully electric vehicles and stop making hybrid vehicles. They're just worse. They're more expensive and the advantages are just not there. So Mazda wants to copy Toyota 20 years later with a worse technology. So again, it's just Mazda. If Mazda had made it 20 years ago, it would have been awesome, but they're too late as always, so makes no sense. But yeah, I mean, technologies of internal combustion engines for the future, there are very relevant ones. There are ones being implemented today, like the Hyundai one, like the Toyota one, like the Suzuki. But it's probably, this is the last of it. It's not gonna be implemented anymore. New technologies are not gonna arise, put it simply. So, it's a little bit of a shame, but not too much. But I wanted people to know some of the changes that were being made today that, in my opinion, were pretty awesome. And I hope you get to experience some of the cool things that were happening at the world. So that's it.